everyone you for joining us for today's webinar. My name is Krunal Kayas and I am the Assistant Professor in Aeronautical Engineering Department at Parul University. Parul University is the leading provider of innovative graphene. Today we are presenting a webinar titled as Static and Dynamic Analysis of Aircraft Wing Using Composite Materials. It's presented by Mr. Smith Kayas. Just a title, little housekeeping. Before we get started, if you have any questions during the presentations, please type them to my numbers, notice my numbers, 9974065420. I will bring them up and during the presentations, and we will also have time for questions at the end. Now, without wasting time, we will go for Mr. Smith Kayas. Our presenter today is Static and Dynamic Analysis of Aircraft Wing Using Composite Materials, with knowledge and expertise on subjects. Mr. Smith Kayas.
Thank you for introduction, Kunal sir. I'll just like to proceed further with giving a small introduction regarding myself. My name is Usmit Kayast. I am working as a technical recruiter at Horizontal as of now, that is in Vadodara, and I am a PU alumni. I have passed out last year in 2020 from Parul University. So going ahead, I do have a topic to be presented here, that is static and dynamic analysis of aircraft wing using graphene. So here the composite material which we were talking about today was graphene. Okay. So moving ahead, topics that would be covered today for this session would be the abstract, that the suppositions we are going to take ahead, whether we need to consider these parameters or not. Okay, and moreover we will be talking about the aim and objective, what we are going to discuss today. Okay, and we will be introducing and having a small brief about what objects we are going to study on, what are their parameters, how they are going to be scaled using different things. Okay, and we will be talking about the materials used and the methodology by which we are going ahead through the analysis of both static and dynamic reasons. Okay, so moving ahead, first of all, I would like to help you out with defining what is a static and dynamic force or a load. Okay, since we are going to work out on static and dynamic part. Yeah, so since we are going to work out on static and dynamic part, so I would just give a small introduction or a brief regarding this terms. Static is nothing but when a load has been applied, but it remains constant, or it does not move. Okay, as presented in the image as of now, you could see that a building is standing over the top. We are applying force on the ground. Okay, the building is standing over there, gravity is working out in the downward direction, but there is no change in the ground, right? The ground is being stable at a location, and there are no changes in the position or direction of the ground. Okay, the ground is the one which is taking ahead all the forces. Okay, so there are no changes in size, position, as well as the direction. Okay, so I hope that gets clear. We are working out on something where the position does not change even if the load is been applied. Okay, whereas talking about the dynamic part, as you can understand through the name itself, dynamic means changes or movement into something, right? So as we can see that if we are applying load to anything, that is changing its magnitude, is changing its direction. If you talk about this person moving this car, if we talk about a pendulum moving, if we apply force once, it's a dynamic load or force that we are applying over the same. Okay, and if we talk about what we are going to work out and discuss ahead on this the same, that would be the analysis that is going to be tackled on regarding static and dynamic. Okay, so we'll be checking. You all would be mostly knowing that the wings of the aircraft are being attached to the fuselage. Okay, that is the circular center part. Okay, so we'll be talking about how this forces impact statically. Fuselage is not going to change its shape. The wing is also going to be in the same position, right? But there would be the tip and the front, extendable part of the wing, which will be encountering a much larger force onto it. Okay, so there we would be able to see multiple changes while pressure and other things would be acting on this airfoils. Okay, so the main objective that we are having today is to work out on a airfoil that is 648-210. Okay, it's a super critical airfoil that I would like to help you out with, and we'll be doing sizing will be done by using classical engineering theories and the analysis of the structure which has been optimally designed. Okay, we'll be working out and checking on the strength and stability criteria. Okay, and moreover, since a wing is not only the outer surface, it also consists of ribs and spars that we talk about. Okay, so we'll be talking about the same as well, that how ribs and spars are acting and ultimately taking ahead the loads onto them, and how it is able to sustain or be in the same position while forces are being acting onto it. Okay, and moreover we'll be talking about the composite materials that are far better and uh, revolutionary in terms of upcoming technologies. Okay, so what aim I have came up with regarding this presentation is, I was looking forward to help out people understand that not only metals but even the composite materials, or you can say materials that are not much way used or has not been introduced right now in the market, are way out more strengthy, comfortable to use, and are having much more uh, properties that could be enhanced, and we can learn a lot of things regarding them. Okay, so the main objectives here are mainly focused to study about graphene and the static and dynamic analysis that we are going to see using both hand calculation method or the formulas, and I would be also helping you out with few of the software models that are being presented further on. Okay, and then I do have a small comparison of uh, it is not fair to directly say that graphene is the ultimate material or composite materials are only the materials that can be worked out with, right? We need to compare them and check out that whether these are the materials which are going to help us out, or do we need to make few more changes. Okay, so we'll be comparing them with dura aluminum and wood. These are the both things that are being commonly used in an aircraft earlier as well and now as well. Okay, so moving on, I would like to start from the basic part, giving introduction. We all know that a wing is the only thing, and utmost required thing that is used to generate lift. Okay, so just to help you out with a small definition regarding the same, wing is a surface used to produce an aerodynamic force normal to the direction of motion while traveling in air or another medium. Okay, which helps out giving a flight or a lift to the object. Okay, and specifically if I talk about anything that gives a shape to a wing, it is called an airfoil. Many of us are now aware about it, that airfoil is the one that helps us out throughout these sessions, that airfoil is the one which gives the basic shape to the wing, and then later on the ribs and the spars and everything comes into action, and the outer skin as well. Okay, so the first word, as we all know, since the history started, that it has been extended from the foremost limbs of the bird, but what was extended to include the wings of insects as well, to make out a better difference. We started since a long time, 200 years back, with the first attempt, and right now we are in a much better way, or having a much better goal to pursue further on. Okay, so wing is an extremely efficient device, I would like to say, to generate lift, and it is equally required for aerodynamic quality expressed as lift to drag ratio, which is a basic function we use for uh, lift generation. So mostly the common use of wings that we use it for deflecting of air downwards. Uh, you would be knowing about it that wings are having this kind of shape, and they do have ailerons and other things to be deflect the air downward, and they would be giving a push it upwards. Upside down wings are being used and to produce force downward so that the object can take a lift in the upmost direction. Okay, talking ahead again about the airfoils, they are built in many various shapes and sizes. Okay, if we talk about the design, they could be designed according to the size of the aircraft. Okay, and moreover, they are looking forward to be controlled using operating speeds, having amount of lift generated and balance that is being needed to the whole aircraft. These are the only key feature or key uh, thing that we are using to generate the lift and control the elevation of the aircraft. So these are the only things that we are using on the basic terms. And moreover, both the leading edge and the trailing edge are a part of wing itself. So one or the both edges are being tapered so that the wing is narrower, and that could give a pure tip towards the fuselage. So as we know that it is smaller, it is having less width towards the end point at the first part and gets huge regarding the second part. And moreover, we all know that it is containing the fuel as well. So it is quite hard to judge regarding how what kind of weight it is going to hold on and what kind of forces would be applied on the same. Okay, and moreover there are parameters to be considered for wing tip as well, that should it be square one, should it be rounded one, should it be in a eagle shaped wing, or should it be in other xyz form, right? So we'll be taking ahead what kind of wing we will be considering ahead here. So just to help you out, we are working out with a dihedral. Just to let you know, dihedral is a cross v shape that we are using. Most of you would have seen it in aircrafts like mostly flying above 600 kilometers per hour. Okay, wherein they are using y-shaped, opposite y-shaped wing. They are using somewhat like this. I hope it is visible. So they are using we are using dihedral angle here that affects the lateral stability so that the aircraft remains stable at higher altitude as well. Okay, so moving ahead, talking about the part of the wings, I would like to say that you can say the spars are the wing skeletons that we can talk about, and moreover, they are the principal structure of the wing. Okay, just to help you out, I do have an image with me as of now. I hope you are visible to see able to see that the green part over there, which is mentioned as a spar, is the horizontal part, which is giving horizontal balance towards the all over length of the wing that we are having from the fuselage to the other open end. Okay, and whereas it parallelly runs through the lateral axis of the aircraft from fuselage towards the tip. Okay, so wherein the spars may be of metal, wood, or any of the composite materials, because they need to be light. As we know that fuel is going to be get filled in over there, it would be gaining much of the uh, weight over there. So most of the time they are looking for something which is lighter in weight but is sustainable at some point of time. Okay, and mostly wooden spars are usually made of spruce. It's a uh, object it's a subject where we can say where it is very light in weight, we can say as light as a cardboard or a ply, but it has a long sustainability to work out with. Okay, and talking about the ribs, that is the inner structure that holds or binds the wing all together. I would like to help you out with the same. Ribs are mentioned over here, that is in the red one. Okay, they do hold the spars at their position as well as strengthen the skeleton of the wing as well. Okay, and mainly they are used to extend from leading edge to the rear spar so that it could hold on for a longer period of time. talking about the shape as well, it will be giving the shape of the airfoil that we have determined. Okay, and more upon, they will be coated across with the skin or the upper foil that is going to be used to cover the wing. Okay, so moving ahead, I would like to go ahead with the structure. We all know what wing is made up of as of now. Mostly the things that are basically covered up here are they are working out with spars, that is the horizontal load balancer or takers. Vertical load balancing is taken by the ribs. Altogether, they form a wing, and the stringers are also there to strengthen up the uh, trailing edge and the backside of the wing, as well as we are using ailerons as well, but we are not considering it into the wing structure as of now, because they are a different component which takes up the wing to a lift position. And upon this, we are using up the skin. So skin are also used with different materials. Okay, so here comes the main part what I was looking forward for. So just to help you out, graphene, I hope few of you would have already given a search to it what kind of material it is. If not, please do Google it out. I would like to say the materials that we are essentially using as a component of aircraft wing, which gives out outcome of conducting a test. They should be at the maximum level, should be on a level that they could be used as an all-rounder throughout the project, or we can say throughout the lifetime of this project life cycle. I'm just talking about using it as an prototype as of now, because it hasn't been come up into the market as an actual aircraft coming out with graphene. Okay, so the world of materials is currently engulfed with research focusing on mass production and characterization of the real world application of this ultra thin carbon film. Okay, it's a material that has been come out with a single layer of carbon, I would like to say, and it is mentioned as graphene. Okay, so if you want, you can just note it down, a single liner. A graphene is nothing but a ultra thin layer of carbon film that is being used and called as graphene. Okay, so moving ahead to other materials that are being commonly used. So it is dura aluminium as well as wood. Okay, so dura aluminium, we all know that 40 to 50% of all aircraft are having or above are having dura aluminium as their concerned or primary material that they are using, right? But why should we switch this materials? Why should we look for something else other than this materials, right? If yes, you are looking forward for something good, why are you looking for that? If no, why not? Why should not you look for something better if that is coming on your way? Okay, and that is the only reason I just came up with this topic, to have you a glance on what technology has grown up to, and what things could be coming up in future if we find a better way out with composite materials. Okay, so coming up for graphene. So just to help you out, you can take a note of it if you want. Just to help you out, graphene is a combination of graphite, and we all know graphite is made of carbon. Okay, and it was named after Hans Peter Boehm and his colleagues. Okay, and was invented by Glim and Novoselvel, who produced it by a Scotch tape method. Okay, and graphene is basically a single atom. I'll come back to that Scotch tape method in a while. Just give me a moment. So graphene is basically a single atomic layer of graphite, which is abundant material which iron allotrope of carbon is made up of, right? With a very tight bonding of carbon materials. Not like graphite that we use in the pencil that breaks very easily. But if we talk about, a graphite slab, or duster shaped graphite slab, if we talk about, and if in case we are applying a Scotch tape, you would be using your butter tape, right, which is a kind of paper kind of thing. If you stick it around onto that slab, leave it across for a while, and take off that tape, dissolve it into a dissolvent like sulfur dioxide or something like that, the scotch tape would be vanishing or dissolving into it. It would be not there, and you will find a very thin layer of carbon. Okay, that is really very thin to be seen. I can say we can see it through a naked eye, but it is really very thin to be taken ahead and shown onto any kind of platform uh, physically. And moreover, just to talk more about graphene, it is the strongest material ever tested in terms of metal industry, or you can say composite materials. That is having a ultimate strength of 130.5 GPa. Just to help you out, it is more stronger than diamond or stainless steel that we are testing right now. It is more stronger, way stronger than diamond, I would like to say. Okay, so the adhesive tape method, or you can say scotch tape method, what I was talking about. All right, so talking about the methodology, or some of the considerations that we have taken ahead, that is, we are going to keep it an ideal study without taking a case or failure based scenario. Okay, we are assuming that it is totally a homogeneous, isotropic, as well as an elastic material to be tested, wherein the spar can carry bending load, and the stress concentration factor has been neglected. So I can say that whenever we are going to apply pressure on the wing, it won't be breaking up. It would just bend a little bit, and we are not going to entertain or take ahead any kind of failures in between. Okay, so just to help you out, I have taken few of the details from a general, you can say, or an online material or a PDF, which was being published by Dimitri A. Dikin and Sasha Stanwokich, Eric J. Zimini, and Richard D. Pinner. Okay, and some of the graphene related theory have been adapted from the source of info. You can just Google them out to have a good review about their paper. So I'll just give you a quick review on what they have actually mentioned there. Okay, so they showed up that how graphene is suitable to use in different materials. In paper, it showed how different methods could be used to extract it, how we are going to show the results in bending material, and how this graphene oxide or that thin layer of paper can be come out with a graph for radius curvature versus the thickness, and also for the tensile strength and the modulus. Okay, so we'll be talking about the tensile behavior of graphene, we can say, where stress and strain curve comes into action, and while applying any kind of temperature or taking it into the temperature, how its graph disease. Just to help you out, it has a lot of temperature taking ability. Okay, and it does not bend really very quickly if combined into multiple layers. Yeah, coming about, as I mentioned about our airfoil, that was NACA 648-215. Okay, uh, so just to help you out, what is a NACA airfoil? Okay, so just to help you out, NACA airfoil 6 series is a combination of shape and the digits and the airfoil thickness that are being used. I will just quickly help you out. I hope my cursor is visible. So we'll talk about the first letter that has been enhanced here. That is the series of nomenclature that has been used. That is series 6 is been here. Okay. Secondly, the airfoil maximum thickness that would be at the second number, that is 4. Okay, and it would be having 40% or 0.4% of cord leading edge. Okay, that would be the maximum thickness of the cord that we are going to use ahead. Okay, and the first digit after the dash, it could be called as the design lift coefficient. Okay, that could be 0.2. Okay, and maximum the drag efficient lift coefficient is we will be getting the minimized drag here. Okay, and moving ahead, the last two final digits are nothing but we all know maximum airfoil thickness, that is into percentage. Okay, so it is not more than 15%. As I mentioned that we are going to use it as a dihedral wing further on. So it would be less than 15% or equal to 15%. And we already know 40% back from the leading edge is already present over there. Okay, so yeah, why did we choose dihedral wing? Okay, so the goal of choosing this was to reduce or eliminate the stress concentrations or hidden undetectable cracks or residual stresses, okay, that were being configured in multiple other wings that we see. Okay, if we use a straight wing that does not has any kind of deflection or something, but it wouldn't have given us the amount of lift that we required to take up any kind of heavy aircraft, or you can say a passenger aircraft even. Okay, moreover we were looking for the loading conditions of the wing that were similar to varying loads, that the loads would be varying as the time passes ahead. Okay, so the wing structure was taken up as a dihedral upward angle wing, okay, which increases the lateral stability while banking of the lower wing was there. Okay, so that it could fly on a higher angle with a higher angle of attack, which gives a better lift in terms of other compared to other wings, I could say. So you can go through this slide for a moment. I will just have a sip. Yeah. So talking about the wing configuration, we have the airfoil, that is the basic NACA 64A210. Okay, and moreover we do have the wing as of now with us, that is the dihedral wing. Now moving ahead, what are the internal uh, parameters that we are going to take into consideration are the wing consists of 16 ribs that are into transverse direction, that is this direction where the wing is elongated towards this way, and we are having two spars to hold up on the longitudinal directions. Okay, and the goal of choosing this are to reduce or eliminate stress concentrations, okay, or any kind of residual or single fracture causing, because there would be a lot of load once it takes off and is getting to a higher altitude. Okay, and a constant variation in the load factor that includes different types of stresses are also taken into consideration. So loading conditions will be similar, but the loads that we are going to present over here would be constant, would be having a constant force over the wing structure. It won't be varying with the time. Okay, so talking about the calculation that we can help or we can do in a better way using the hand calculations over here is calculating the load with L is equal to NW. Most of you would have been knowing this formula. It's the basic one that we are using into aerodynamics. That is, lift is equal to load factor that we are getting earlier from the case itself and the aircraft uh, weight. Okay, I have not mentioned or taken ahead any kind of calculations ahead. I've just given an assumption. You can do the calculation required on your own and can get back to Kunal sir and help him out and take the answers from my end as well. Later on, you can share it across. So if you want, I can show across again the formula. It is L is equal to N into W. Okay, that is lift is equal to load factor that we have taken 1.5, and the weight of the aircraft here is 14,000 Newton. Okay, now we need to calculate what kind of bending forces are going to work on different axes, right? So while we are working out with the forces, we are going to face y directional forces. There are going to be z directional forces as well, right? So we are going to use the formula wherein bending moment about axis z axis is being going to be considered, and the stress would be calculated directly. I would like to say there are no other stresses to be calculated on a different way. Okay, so this is the second equation that you can go ahead with. And for the vibration, last one was for the bending part that you would be able to see in the y and z direction. And talking about the vibrations, or the movement of the wing that is going to happen, you would have to go ahead with this formula. I know you won't have seen this formula much earlier, but just give it a try. Use this formula to look out for any of the real-time scenarios where frequency has been calculated using 1.875 square upon 2x. X is the variable here which you are going to calculate based upon the lift that has been generated. Okay, so you will be using I here for that is wingspan. Okay, E here that is Young's modulus. The second one that is into under root of ELM, right? That is the moment of inertia of the wing. Okay, and M is the mass or the unit length of the wing. Okay, so you can take it as an example that X is the variable that we are having as in 15. Okay, so you can take it L as the wingspan as 15 meters again, and E Young's modulus you are knowing about it, and the mass we already know about it. It's 14,000 Newton. So you can calculate accordingly. Okay, so yeah, coming to the modeling part. So this is a small image that I could fetch out for you. That is for NACA 64821 Okay, this is the basic airfoil that has been generated using multiple iterations, and this is the basic developed component of the aircraft wing. Okay, and moving ahead, I have the 3D modeling wing. As you could see, as I mentioned, there are thousands and lakhs of iterations being measured over there, which are having different geometry as well as different parameters to be counted on. It is into if you can just check out, it is into Z, Y, Z, and X direction as well, and it's a bit of the mark towards X-axis just to help you out. Okay, and here we have taken the parameters as of now just to show you that is into 2 meter. Okay, so yeah, how did the analysis go through? So regarding the analysis part, we all know that the highest load that has been taken ahead is through the end part of the wing. Okay, that would be taking the highest part, and the red here symbolizes the total deformation. I hope it is quite visible. It's the static structure deformation. Wing is on its own position, but only thing is movement is being there. Okay, it's not getting deflected as we have taken an idle condition, but the much highest or the highest force that has been applied over here is on this part of the wing. Okay, and as we could see, the blue part, it has been the least or the lowest affected part with zero load over it. Okay, and if we talk about going ahead with aluminum is if you could just check on this part, the area here for graphene is much expandable or longer, right? Here it is a bit lower than graphene, I would like to say, and the deformation we can say it's getting a bit red this end, and it's getting darker in long way along the way. Okay, and for balsa wood, as of now, we could see that in idle condition it is showing least deformation, but this is the max deformation that it could take, but later on it would be breaking. So this is what it is showing for balsa wood, because it won't be able to take much of the load and will be breaking on very quick basis. So they have the software has not taken it ahead for a longer duration with applying more load onto it. Okay, so it is going to get constrained for this much only, and then it would be breaking down. So we have not accepted that condition or entered that condition into the software. Okay, just to help you out with the final result, how it is going to be or how it becomes or looks like. For aluminum, the permittibility or the deformation remains one, the relative permittibility. And if we talk about the Young's modulus for graphene, it is the highest what we can say. If you could just compare over here, it is 1.66, and here it is way larger than balsa wood. I would like to say. For aluminum, we were not able to come up with a proper, result because there were some iteration problems that were going on with the uh, result to be shown. Okay. If you want, you can take a snap or note it down. I can have it for a minute. All right. So lastly, I did show you up with the calculation. What was the reason that we came up with the graphene? Why did we try it on the aircraft thing? Everything has been discussed. So just to help you out, I would like to say, not emphasizing more regarding the aircraft part or the wing part. I would like to say, as of now, if we talk about graphene, it is a boon that we have discreetly right now in our aerospace field. Okay. And one more thing I would like to add on here is we are using not using graphene as of now. The only reason behind is, Scotch tape method is a very limited method wherein we are able to get only small sheets of graphene, where we are not able to produce it in a longer form, or we are not able to produce it in a large scale, I would like to say. Okay. So once we are able to go through or crack that way, how we can mass produce this material, it could be used out in a various way, I would like to say. Okay. And if we compare about the materials, graphene is stronger than both the materials, I would like to say, in a much good way, if we talk about the aircraft wing specifically. Okay. And moreover, we are using wood and aluminum. They are not bad, but I would like to say, if we get a small change here, we would be able to make a brilliant material and come out with a way better material to work out with. Okay. And what all things you could be doing next to, if you want to take ahead this research or this project ahead, you can do a individual sizing of each and every component, considering all the part for the analysis. As of now, we had considered only the wing, that was the outer part, inner part, that are spars and all these things, right? You can take a consideration of just constructing a landing gear using a graphene. It would be able to take up a lot of load. You can individually take up the components, just analyzing using the fuselage. You can do it for the whole aircraft as well. Okay. Thickness variation, we did not go for it because it was a time taking part. But if in case we are working out with the thickness variation, if we are giving more of the material as an graphene being loaded over a location, it is lighter in weight, we all know about it. But if in case it is having a thickness that could way longer take ahead path towards space crafts as well, I would like to say, since it has a lot of capacity to take heat as well as to take the stress onto its internal uh, design. And since this material has significant properties of conducting electricity, okay, and taking great amount of stresses, and internally within communication and navigation as well. Okay. So I forgot to mention that point. It is a great conductor. It has merely any resistivity to be taken ahead. It could be internally used in the navigation of any of the aircrafts, or uh, we can use it in our smartphone as well. Just to help you out, many of you would be going through tech news now and then. We do come out with composite materials from Qualcomm and all these organizations, right? They are working out with such kind of materials. They have found graphene as a good boon to their industry as well. It's not having at all any kind of resistivity. So if in case it gets attached in your mobile, it would not be released, and you would be able to go ahead with multiple things with the least and minimum thickness in your phones. Okay. So yeah, the references which I had are being given here. If you want, I can help you out and go through it as well. Okay. So that's all from my end. if you have any questions, you can please go ahead with them.
Okay. Done?
Sure. I'm done from my end.
Thank you, Mr. Vishmit Kayas. We will go ahead and take some time for questions.
Sure.
Just a reminder,
Sure, sure.
uh,
No problem.
first questions, any other more ways in regards for exploring other uses of graphite other than using aircraft?
Okay, if we talk about other than aircraft, it could be used into navigation industry. Okay, the panels that we are using into the ships right now to communicate each other, right? They are mostly used with terra-coated materials as of now, right? So graphene, as we know that it is a thin material, light-weighted thing. So we can use this, as a communication device as well. It's reflection, or we can say communication uh, frequency or the magnitude is very low, so you can communicate very easily through across the globe. One satellite has been having accountability to work out with graphene as well. And as I mentioned, across for mobile as well as laptop and other things as well, it could work out for communication as well as internal switching of motherboard, and these things also could be taken ahead as it is a good conductor.
Okay. Now, second one,
Yeah, please.
how much is software-based calculations reliable and relevant to hand calculation?
Uh, See, I would like to say softwares are reliable, but hand calculations are the best that you can go ahead with, because software calculations works on few parameters, and in real life we don't have parameters as in any bird or any kind of unconditional failure comes up, or lightning comes up. Any such kind of things are coming up across and getting into action. We need to figure these things out. So hand calculations are the best way to come out with any of the outcomes, and the result may vary, but I would prefer hand calculations would be the best to go ahead with any calculations. uh, Lastly, just to conclude, we can use software calculation, but they are just for reference, I would like to say. The closer it comes to hand calculation, it would be the best, better one.
Is graphene biodegradable?
Yes, it is biodegradable. As we talk about, it's a carbon-based type compact material. So if in case it get buried into the core or towards the Earth's part, it can get biodegraded within a couple of decades. So kind of graphite thing it is.
Okay. Friend,
Yeah,
thank you everyone. We appreciate you being here. Thank you
I'm
very
really
much,
thank
sir,
you.
for sparing your valuable time. Have a good day.
Same to you. Thank you. Bye.
Bye. Lecture.